Greetings to all of you. The session is regarding intermediate chemistry. If you are preparing for any international entrance and competitive examinations, India is conducting JEE Advanced, JEE Mains examination for the admission into IIT and NIT stream. In addition, NEET chemistry will be conducted, NEET exam will be conducted all across India. That is for medical entrance exam. Telangana government and Andhra Pradesh government are conducting the exam, that is MCET examination for BTech admissions, right? So that is also the technical domain. In addition, government organizations are conducting the exam that will be very much fetching for your career opportunities in the government sector, right? In that, general studies common question paper will be found. In that, general science content will be available. The session what we are discussing is fetching for that kind of preparation as well. Let's go with the first content related with the Nobel winning quantum dots, right? So here 2023 Nobel Prize is accorded for the invention of quantum dots. This is the outstanding contribution for the research in terms of chemistry, so that it is accorded with the Nobel Prize. Let's see about what is quantum dot and who are accorded with the Nobel Prize for their contribution for the research in the field of this chemistry and in specific to the nanotechnology. Quantum dots can be seen as one of the milestones for the whole field of nanotechnology, right? So quantum dots, invention of quantum dots is said to be a kind of milestone, we can say, especially in the field of nanotechnology. A tiny particle diameter matters for the exceptional properties, and these quantum dots are invented by this kind of research exploration carried by these three scientists together. One is Mongi G. Bovendi, Massachusetts Institute of Technology, MIT, Cambridge, MA, and that is available, that is present in the United States of America, right? Louis E. Bruce, Columbia University, New York, USA. So Alexei Yokimov, so nanocrystal technology, he is expert in nanocrystal technology, New York, USA. So these are the three scientists together accorded for the Nobel Prize in the field of quantum dots, right? So for their outstanding contribution and exploration in this quantum dots nanotechnology domain it will be. So these three scientists together worked a lot, and they gave the what useful research in the field of this kind of chemistry, right? Let's see here. These are the eminent scientists who are accorded with the Nobel Prize. Just now we gone through their portfolio. Mongi Bavendi, Louis Bruce, and Alexei Ekimov. These three scientists together, discovery and synthesis of quantum dots worked a lot over here. That's why Royal Swedish Academy of Sciences accorded Nobel Prize for these three scientists together. Nobel Prize in Chemistry 2023 reward discovery and development of quantum dots. Quantum dots are the nanoparticles, so tiny particles, their size determines their properties. So if you go with the bulk sized particle to the nano sized particles, they are used to morpholize their exceptional change in the properties, right? So here the diameter matters here. So earlier the nature of the element, electrons resides in the valency shell, these many concepts come into the picture in order to explain about their properties. Any kind of atom or any kind of molecule is explained in terms of its valency electron count, so that its properties purely relies on its electronic configuration. That is the fundamental phenomenon everybody knows. But in terms of nanotechnology, diameter of the particle matters, right? Nanoscale materials are having exceptional properties, entirely new properties. Same material under bulk condition, if it is the insulator, if you are making into a nano size, that will become an electrical conducting material. This is the way diameter matters for its morphology in the properties, right? This is smallest component of nanotechnology now spread the light from the televisions, LED lamps, can also guide surgeons when the removal of tumor tissues and many other things. So these are the kind of inclusive applications related with these nano-sized particles called quantum dots. They may be applicable in television displays, light emitting diode lamps. So there we can use quantum dots. And moreover, in the tumor tissue analogy, right? The patient who are suffering with the cancer or else any kind of tumor, malignant tumors are present. So that kind of removal and also analysis can be carried by means of these quantum dots. Everyone who studies chemistry learns that elemental properties mainly depends upon their electrons, but in terms of these quantum dots, here quantum phenomenon arised whenever nano dimensions we are going with. 1 billionth of the meter is said to be on nano scale, nanomaterial, and at that condition here quantum dot is also the part of that nanotechnology. So the Nobel laureates in chemistry 2023 have succeeded producing particles of smaller in the size determined by quantum phenomenon. These are called the quantum dots, now of the great importance in the nanotechnology. Because of this extent of significance, these are accorded with the Nobel Prize. They are finding wide range of applications over there, right? Let's have a small glance about all the scientists who are accorded with the Nobel Prize in Chemistry for quantum dots invention and research in 2023 by Royal Swedish Academy. Uh, Alexei Yekimov, he started his journey of research in 1980s, succeeded creating size-dependent quantum effect in colored glass. A quantum effect is observed in the colored glass by the scientist Yekimov, right? The color came from the nanoparticles of copper chloride, and Yekimov demonstrated that particle size affected the color of the glass by a quantum effect. So the color, whatever exhibited by the glass, is purely because of the quantum effect which is present, which is exhibited by the nano-sized particles. So here colored properties also changed. Whenever you are going with the bulk to the nanoscale, the color properties also entirely change because of quantum effect. That first studied by the Alexei Yekimov in the year 1980s. A few years later, Louis Bros was the first scientist in the world to prove size-dependent quantum effect in particles floating freely in the fluid. Any kind of material which is moving, having mobility, that is said to be a fluid, right? Flowing tendency material is called fluid. In that moving material, so here because of the tiny size of the particle, they are used to exhibit the quantum effect. That phenomenon, that correlation is first observed by the in the entire world, it is first observed by the scientist Louis Bros, right? In the year 1993, Mongi Bawendi revolutionized chemical production of quantum dots resolution among the perfect particles. This high quality was necessary for them to utilize in the application. So the concept was introduced by Ekimo, and Bruce was expanded the exploration of how the quantum effect is size dependent, diameter dependent in the moving particles like a fluid type of material. And whatever concept they got introduced, that was scaled, whatever that obtained in the form of product in the bulk yield by the scientist Mongi Bovendi in the year 1993. Because of this reason, large scale preparation of these materials, their exploration, their compound synthesized compounds are ready for the application oriented methods. That's the reason why all are having their own way of contribution towards this kind of research. That's the reason why these three are together accorded with the Nobel Prize for these quantum dots. Quantum dots now illuminate computer monitors, television screens are brightened by this process. They all add nons to the light of some LED lamps. Biochemists and doctors use them to map biological tissues. In order to analyze the biological tissues, in order to display the television screens and LED lamps, all these are equipped by the phenomenon called quantum dots and quantum effect used to give that kind of glorious colors and medical curation phenomenons as well, right? So quantum dots, what quantum dots will do, let's go with that. Used to produce the inextensive industrial quality white light. So whatever quality light, quantum effect, quantum dots having natural tendency, here you can clearly observe, they are having natural tendency to generate the light okay, which is highly luminous in nature, and that industrial quality, highest quality light can be generated by means of these quantum dots, marked improvement over the traditional LED password integration by dots ability to absorb and emit any desired wavelength, right? So here they having tendency, quantum dots are having tendency, a marked improvement over the traditional LED phosphorus. So light emitting diodes having natural luminescence, quantum dots being these particles are nano-sized in nature, so that their ability is still high. Comparably, their efficiency of luminescence or brightness is extremely large. Produce white light by intermixing red, green, blue emitting dots homogeneously within the phosphor, difficult to accomplish with the traditional LED phosphor setup. Okay, so most probably quantum dots are able to lit up with the bright white color light. Okay, so they can be blended with either red color, green and blue, so that we are able to achieve so many other types as well. This is the way light emission or quantum effect used in various fields. Now, in a glance, we will go with the quantum dot applications. Whatever invention is there without any application, that may not be sensible. That will not create any sense of implementation. So that applications plays a vital role for any invention. That's why we will go with the applications of quantum dots. Photovoltaic devices can be equipped by these quantum dots, so that solar cells manufactured which is of high renewable energy source. Biology, in terms of biology, you can use as a biosensors in order to identify living organism action, functioning, efficiency. Everything can be monitored, analyzed by means of biosensors which are equipped by quantum dots. And biosensing imaging will be there, that is also made up of this kind of quantum dots. Light emitting diodes, just now we gone through that, they are having tendency to brighten the screen, so that display screens can be equipped by quantum dots, LED screens we can say. Quantum computation will be there. So in addition to this kind of scientific perception, you can blend up with the computational softwares as well, so that quantum computation, where you can use these quantum dots, right? So wherever the blend of science and the technology, always that will be flourished, because science is having the fundamentals, and the technology will use to explore in the maximum extent. Applicability is given by the computational technologies only, so that here quantum computation is the kind of blend of this quantum dots scientific perception with the technical aspects, right? So quantum computation is more important. Flat panel displays we can say. So just now we gone through LED displays like television, desktops and laptops. Wherever you are having display system, flat panel displays are equipped by these quantum dots. Even mobile phone is also having flat display, so there also you can utilize memory elements in order to store the data, in order to transfer the data, in order to memorize the data. Memory chips, memory content devices will be available. In that also you can embed with these quantum dots. The quantum dot technology can be applied over memory elements as well. Photo detectors, photodetectors are nothing but what kind of analyzing devices whichever present working under light conditions are called photodetectors. So light related reactions, related capturings, light related findings if present, those kind of phenomenons are designated as photodetectors. So there also we can use the technology of quantum dots. Even lasers having high intensified light, that laser technology is most advanced and moreover important in the medical field and science technology. Everywhere you can apply major laser rays. So these are also having applicability of quantum dots over there. So this is a kind of application related with these quantum dots, multiple applications you can find. That's the reason why the scientists who contributed for this kind of domain, this track, they are accorded with the prestigious Nobel Prize for this. Move on to question number 2. Question number 2, collected from Cambridge Assessment International Education. Nitrate decompose when heated. So always nitrate having natural tendency to go for decomposition upon higher temperature conditions, right? Whenever hydrated zinc nitrate is heated, oxygen gas is given up. Describe the test for oxygen. Okay, so here zinc nitrate decomposed to give oxygen. They only saying what is the reactant, what is the product. But the thing is, whatever oxygen coming out, that oxygen to be identified, to be tested. So how can we analyze bubbles are coming from the test tube, for example? You can't analyze whether it is oxygen bubbles, hydrogen bubbles, carbon dioxide bubbles. So many gases are there, no? So that the thing we need to find is confirmation test. That is for oxygen element, oxygen molecule. Okay, so what test you are going to do and what observation you saw. So both the things to be addressed here, right? And the next question is complete the equation for the decomposition of hydrated zinc nitrate. Hydrated zinc nitrate is nothing but zinc nitrate hexahydrate. Whenever zinc nitrate hexahydrate is heated, first of all, water will be vaporized, so that need not to go for decompose this water. Whatever water is evaporated, put a 6 number of moles over here, that finalized. Another term is about zinc nitrate. Zinc nitrate decomposed to give three components. One is zinc oxide, another is nitrogen dioxide, third is oxygen. Only the thing we have to do, our work is about, we have to count according to the law of conservation. We need to go for the number of atoms left side equals to number of atoms right side. So that put the coefficient in front and it will be finalized to get the balanced equation. This is the way we can answer. So let's see how can we answer both the questions. So initially what he is doing, zinc nitrate is to be heated so that oxygen gas is evolved. In order to burn this zinc nitrate solid can be taken upon rising the temperature, that will be decomposed to zinc oxide, nitrogen dioxide and oxygen. So that 2 moles of zinc nitrate upon thermolysis, so that it used to decompose 2 moles of zinc oxide, 4 moles of nitrogen dioxide and oxygen will be evolved. This is the way you can go for the chemical reaction. Now the thing is, oxygen to be identified. Oxygen to be identified. In order to identify the oxygen, in which test tube you are doing the experiment, there is obvious oxygen gas bubbles will be evolved at the neck of this test tube. Wherever you are experiencing oxygen bubbles, there you have to place a lighting match. So lighting splinter can be inserted over there. So whenever lighting splint is inserted, if its brightness increased or else it is continuously burning in the same manner, that indicates whatever gas evolving is the oxygen. Oxygen is the fuel of any kind of burning tendency. So if you're trying to burn the trying to lightening the candle without any oxygen in the room, it's 100% impossible, we can say, because oxygen is a fuel for burning. Oxygen required to burn any gas, right? Carbon dioxide used to stop burning, oxygen used to facilitate the process of burning. That's the reason why if your lighting splint is inserted over there, it is continuously burning in the same manner. That indicates the whatever gas coming is the oxygen. So the ignition is carried and the continuation of that ignited match is also possible whenever oxygen is present in the test tube. This is the way, very simple test you can notice. So the test is you're putting that splint containing the light over there at the neck of test tube where the oxygen gas is evolving. The observation what you saw is, so that is continuously lighting up, that is becoming a luminous one for the longer time, purely because of the presence of oxygen gas in the test tube. This is the way test and observation got carried. We will go with the balancing of equation. Always balancing of equation follows law of conservation, right? So in order to go for law of conservation, left side how many atoms, right side equal number of atoms to be present. So that zinc nitrate of 2 moles are taken. Whenever 2 moles of zinc nitrate were taken, again you have to put over zinc oxide like this. So if you go with the NO3 taken twice, if NO3 taken twice is there, you can count the number of nitrogens first. Nitrogens are NO3. one nitrogen repeated for 2 times, and this 2 can be multiplied with this 2 coefficient. 2 2s are, it will be 4, so that nitrogens are 4 over here. So we put over 4 nitrogen dioxides like this, and oxygens are mentioned here. 6 water will be evaporated. Here it will be a kind of crystallized water is there. So here water for crystallization you can find here in this, but after the rising temperature, whatever water is there that got evaporated, it is gaseous one, vapor water you can notice. Though 6 moles converted into 6 moles only, but here is the water of crystallization, here is the water of vaporization, right? This is the difference you can notice, phase change you can observe. And let me go with the oxygen atoms. Zinc completed, nitrogen completed, no? Go with the oxygens counter. Here, oxygens are 3 times and repeated for 2 times. So that multiply 3 with 2, so that it will become 6. 6 can be multiplied with 2 again. 6 2s are 12. So let me count oxygens in the right hand side. 2 oxygens are there in zinc oxide, and here 4 coefficient repeated O2. So here 2 can be multiplied with 4, so that 8. 8 plus 2, 10 oxygens finished. 10 plus 2, 12 oxygens. So whatever there in the reactant, same extent of oxygens found in product as well. 6 water remains as such, need not to touch this one. So these many atoms got sufficiently balanced if you are introducing 2 coefficient for zinc oxide, 4 coefficient for nitrogen dioxide, and 1 coefficient for O2. This is the way equation can be balanced. So that entire question number 2 got addressed over here, right? This is for question number 2. Move on to question number 3. Question number 3 is collected from 2023 J advanced question paper 1 question. It will be, for the helium place, our transition takes place from the orbit of radius 105.8 picometers to orbit of radius 26.45 picometers. The wavelength of the emitted photon during the transition is, what is the wavelength of emitted photon during the transition to be determined? That is indicated as 30. Okay, here the data is provided. Bohr's radius is given by A, and whose value is 52.9 picometers. This is the Bohr's radius A. Then Rydberg constant value, Rydberg constant denoted with RH. RH factor is given by 2.2 into 10 to the power negative 18. This is required for our problem solving. Planck constant is known to you, 6.6 into 10 to the power negative 34. Speed of light is also known, that is C, 3 into 10 to the power 8 meter per second. This is the way entire data is provided for question number 3. Let's try to solve this one. Helium transition takes place from the orbit of radius 105.8 to the orbit of radius 26.45 picometers. The wavelength of emitted photons, lambda value to be identified in nanometers. In order to calculate that, we have the formula, radius is equal to 52.9 into n square by z picometers. R is equal to 52.9 into n square by z picometers. That is the value. R is nothing but radius, no? Radius transition takes place from the orbit of radius. The initial radius is given by 105.8 picometers. That 105 radius can be taken over here. 52.9 n square by 2. Why it is 2? Because helium atomic number is taken as 2 only, no? So this is about what radius formula. Radius formula is known, and in this we identified this too. If you go for the calculation of this entire thing, so n square value is calculated, that is taken as 2. So remaining all the values are known, only n2 can be calculated, that is taken as 2. So after that, second radius is given. So here initial radius is 105.8, second radius 26.45. So if you substitute that value 26.45 and 52.9 remains same, n square is unknown, by 2 remains same. So that if you go for this calculation, the value is the n1 value is obtained over here. N2 is the excited one, N1 is the ground state. You can notice N1 value is taken as a 1, N2 value is taken as 2. This is the way values are calculated. Delta E, change in energy is equal to RH Rydberg constant into Z square 1 by N1 square minus 1 by N2 square. Delta E is nothing but change in energy is equal to Rydberg constant into Z square 1 by N1 square minus 1 by N2 square can be taken. Okay. So delta E, we have E is equal to H nu. E is equal to H nu formula is known to each and everyone. E is equal to H nu can be replaced with E is equal to Hc by lambda. Is equal to Hc by lambda also we can write, because nu frequency is equal to c by lambda. C is the velocity of light, lambda is the wavelength of light. Okay, so here Hc by lambda is equal to Rh into Z square into 1 by N1 square minus 1 by N2 square. So this is the formula for energy transition, right? H is the Planck's constant, that value is given to you 6.6 into 10 to the power negative 34. This value can be taken as such. C is the velocity of light. This is taken as 3 into 10 to the power 8. Lambda is only the requirement to be calculated in nanometers, no? So that place aside. Then Rydberg constant is known to you 2.2 into 10 to the power negative 18. That is given within the data. Rydberg constant is given, Planck constant is given, C value, speed of light is also given. Bohr's radius is given. Bohr's radius is 52.9, that is also given. Okay. So Rydberg constant value was placed. Z is the atomic number of helium, and 2 square can be taken. 2 square directly I am writing as a 4. Okay. N1 value is taken as 1, so that 1 by N1 square. So 1 by 1 you can put over, and 1 by N2 square. N2 value is 2, no? So that 1 by 2 square, so that 1 by 4 you can write it. This is the way entire equation was written. 6.6 into 10 to the power negative 34 into 3 into 10 to the power 8 by lambda is equal to 2.2 into 10 to the power negative 18 into, if you go for the LCM for this one, 4, what you can write, 4 minus 1 by 4 you can write. 4 minus 1 is nothing but 3 by 4. So 4 into 3 by 4, 4 get cancelled out. Okay, so if you cancel 4, then the value will remain, so 2.2 into 10 to the power negative 18 into 3. So here remaining all the terms are known except lambda. So lambda can be calculated at 300 angstroms. If you want to convert angstroms into nanometers, so 300 angstroms equals to 30 nanometers. This is the way problem can be solved over, and lambda wavelength value is designated as 30 nanometers. 30 nanometers is taken. So this is somewhat lengthy problem, but we have to go for the step-by-step calculation like this. So first of all, we have to know the formula for the radius. Radius is equal to A into N square by Z. A means what? Bohr's radius, that can be taken as 52.9, and N square to be calculated. Z is the atomic number. So this is for radius. 2 radius we have, so that for 2 times you can go for N2 value, N1 value. After getting the change in energy to be calculated by using the simple formula, Rydberg constant into Z square by 1 by N1 square minus 1 by N2 square. This is the formula. If you put over, you will get the lambda value over here. So for question number 3, 30 nanometers is the correct answer. Move on to question number 4. Question number 4 is collected from JEE Advanced 2023, paper 2, question it is. Again, it is the problematic session only, and you can go with the analytical part, especially volumetric part it will be. And you, if you observe, osmotic pressure is taken, so that it is also the part of colligative properties, we can say. Colligative properties, problematic session, physical chemistry section. 50 ml of 0.2 molar urea solution, whose density is given by 1.012 gram mole liter inverse at 300 Kelvin, is mixed with 250 ml of solution containing 0.06 grams of urea. Both the solutions were prepared in the same solvent. The osmotic pressure in tar of the resulting solution at 300 Kelvin is osmotic pressure value to be found at 300 Kelvin. It is expected to be written as, we have to go for the calculation to get 682 as the correct answer. Molar mass of urea is given as 60 gram per mole. Gaseous universal gas constant R is equal to 62 liter torr Kelvin inverse mole inverse. This is for R value. R value different units, different value will be there, but liter torr Kelvin inverse mole inverse, it will be 62. Remember this. Delta mixture of H for what? Enthalpy. So delta mixture enthalpy is taken as 0. Delta mixture volume is taken as 0. So this is the way data is provided, and we have to go for the calculation of the problem. Number of moles of urea. Number of moles of urea is given, that is 0.2 moles. 0.2 moles of urea is given. Weight of urea is equal to what? Weight of urea. So here moles is equal to weight by gram molecular weight. That is well known to each and everyone. Moles is equal to weight by gram molecular weight. If you want to calculate weight of the substance, so weight is equal to number of moles into gram molecular weight you can put on. So moles are known 0.2. Molecular weight of urea, just now we saw molecular weight of urea is given as 60. So that 0.2 multiplied with 60, you will get 12 grams. 12 grams of what? Weight of urea you got. Then weight of the solvent. What solvent we have? Here urea solution was taken. Generally it is mixed up with water only, no? So weight of the solvent is given as 1000 grams. Okay, so here weight of urea is nothing but weight of solute, because whatever you're mixing is called solute. Whatever miscible, in order to mix that one, the bulk quantity material is said to be solvent always. So that solvent was taken as solvent was taken as 1000 grams. 1000 grams is equal to 1 kg of solvent. In general, we have to go for, because wherever you are calculating molality, wherever the solvent is, in general, you can go for 1000 grams only. Then weight of the solution. So weight of the solute is known, weight of the solvent is known. Then weight of the solution is equal to 1000 plus 12, so that 1012 grams it will be. Solution means a solvent plus a solute only, no? Solvent is 1000 grams, solute is 12 grams, so that mix up 1012 grams of weight of solution we got. Then volume of the solution is equal to volume of the solution. In order to calculate the volume, what is the formula of density? Density is equal to mass by volume, no? So mass by volume is equal to density, but you want to calculate volume, then volume is equal to mass by density. Just to replace the formula, volume is equal to mass by density. Mass is given as 1012. Density, let's go with the density. Urea density is given as 1.012 gram mole liter inverse. So that is known to you. So 1.012 is the density of that urea. 1012 by 1.012. If you go for the calculation, that volume of the solution is 1000 ml. You got it? 1000 ml. Okay. 1000 ml solution, in that 1000 ml solution, urea number of moles is 0.2 only. But 50 ml solution, we have to go for the calculation. They are considering 50 ml of urea solution, right? If 1000 ml contains 0.2 moles, 50 ml urea solution contains how many moles? So that go for the cross multiplication. 50 multiplied with 0.2 and divided with 1000. 0.2 multiplied with 50 by 1000. So that the value is 0.01. What is the final value? 0.01. This is the number of moles for 50 ml of the solution. Okay. Moles of urea in the other solution is given by 0.06 by 60. Moles of urea in other solution. Moles of urea in other solution is given by 0.06 by 60. So then it will be 0.001. Okay. Then in order to calculate the concentration of the solution, here we have 0.01. For 50 ml number of moles are 0.01 and 0.001. So number of moles of urea is another solution is given by 0.001 by 300 by 1000. because here 300 is the temperature provided. Okay, 300 by 1000 can be taken. Okay, so if this is the equation 0.01 plus 0.001 by 300 by 1000 if taken, so if you go for the calculation of this entire thing, the concentration will be 0.0366. This is the mixture solution. Because two urea solutions we have, 50 ml of 0.2 molar urea solution was given. It mixed with 250 ml of the solution containing 0.06 grams of urea, right? 0.06 grams of urea, number of moles are 0.001. So because we have two solutions, no? So two solutions if mixed, the mixture concentration is given as 0.03. This is the mixture concentration. Now we have the formula according to the colligative properties. This osmotic pressure pi is equal to CRT. Osmotic pressure pi is equal to CRT. C for what? C for concentration. Whose concentration? Concentration of mixture of urea solution. Okay, that concentration of mixture of urea solution is taken as 0.0366. R is the universal gas constant whose value is provided here. What is the value? 62. That is R gas constant 62 is their temperature. At what temperature you are calculating this? 300 Kelvin. Temperature is taken as 300 Kelvin. So that put the 300 here. Concentration into gas constant into 300. If you go for the multiplication, you will get 682. What is the 682? This is the osmotic pressure. So that is only they're asking osmotic pressure 682 is required, that we got over here. Okay, so this is the way. Question number 4, correct answer is 682. Let's move on to question number 5. Question number 5, at what temperature is the root mean square RMS speed of neon gas atom is equal to RMS speed of helium gas atom at minus 33 degrees centigrade? Okay, this is the question related with the root mean square velocity. So it is the gaseous state, especially the content is related with the gaseous state. And RMS velocity, they are asking for the noble gases neon and helium, that is to be taken. At what temperature root mean square speed of neon gas atoms is equal to root mean square velocity of helium gas? Right, the temperature provided is minus 33 degrees centigrade. Atomic mass of neon is 20.2 and the atomic mass of helium is 4.0. If this is the data provided, at what temperature you have to go for the calculation, that is taken as a 1212 Kelvin, 1212 Kelvin. This is the requisite answer for question number 5. Let's move on to how to solve the question, right? Temperature of the helium. Temperature of the helium is mentioned as the T helium, that is given by minus 33 degrees centigrade. Helium temperature is given by minus 33 degrees centigrade. If you want to convert centigrade into Kelvin scale, so here whatever value you have, temperature plus 273 can be added. But here the temperature is given in negative 33 plus 273. What happens? You have to go for the subtraction. 273 minus 33, that will be 240 Kelvin. Okay. Within the data, they provided atomic mass of neon is 20.2. Velocity, RMS velocity of neon is given by the formula. So this is the known formula. This is the empirical formula, we can say. RMS velocity of neon is equal to root of 3RT neon by M of neon, right? So root of 3RT neon by M of neon, where R is the universal gas constant. Everybody know about this one. T and E is nothing but temperature of neon. At what temperature neon is taken over here? The RMS speed of helium is equal. This is for what? RMS speed of neon we gone with. Then RMS speed of helium we have to calculate, that is under root 3RT helium by M helium. It's given that. So if you go for comparison between VRMS of neon is equal to VRMS of helium, within the problem only they mentioned. What they mentioned? At what temperature root mean square velocity of neon and RMS velocity of helium are equal? Okay, both are equalized. So that what happens, I can write it as Vrms neon is equal to Vrms helium. This is the equation. So Vrms of neon is known to you. That is under root 3 RT by neon by M neon is equal to under root 3 RT helium by M helium. This is the equation. Okay. Here the common terms get cancelled out. Right side, left side, whatever common things are there, you can compensate. Under root 3, both sides we have, so that cancel out. Universal gas constant is there. Temperature neon, temperature helium can't be cancelled. Both are different. This M neon, mass of helium, both are different. So that you can't cancel it. Only under root 3R you can cancel for both the sides. Then temperature of neon by M neon is equal to temperature of helium by M helium. Temperature of neon, so this is only required at what temperature they are asking. So that temperature of neon is equal to temperature of helium by mass of molar mass of helium into molar mass of neon. Okay, temperature of helium is given, that is minus 33 degrees centigrade. On Kelvin scale it will be 240 Kelvin. Temperature of helium is 240 Kelvin. Then molar mass of helium is 4. That is given within the data. Within the problem they mentioned molar mass of helium is 4. Molar mass of neon is 20.2. This is also known to you. So 240 by 4 into 20.2. If you go for the calculation of these entire things, temperature of neon is equal to 1212 Kelvin. That answer is provided in the option number 3. For question number 5, option number 3 is the correct answer. You can put 3 as the correct answer. Move on to question number 6. If the radius and the energy of the second Bohr orbit of hydrogen atom R2 and E2 respectively, the radius and energy of third Bohr orbit and energy respectively. Okay, second Bohr's orbit and radius and energy are provided. Third Bohr orbit energy and radius to be calculated. 9 by 5 or 9 by 4 R2, 4 by 9 E2. These are required answers. We will go for the calculation. According to Bohr's postulates, radius can be calculated by n squared h squared by 4 pi square mze square. This is the formula. Let me repeat. Radius of the Bohr's orbit is equal to n squared h squared by 4 pi square mze square. R2, second Bohr's orbit is equal to R1 into N2. Second Bohr's orbit is equal to R1 into N2 if you write. Okay, so that you can substitute the value as R1 into 2 square is equal to 4R1. 2 square is 4R1, 4R1. So that is for R2 is equal to 4R1. R3 is equal to R1 into N2. R1 into N2. So here the value will become R1 into, for this n value it will be 3 because R3, right? So that 3 square will become 9. So R3 is equal to 9R1, R2 is equal to 4R1, R3 is equal to 9R1. R2 is equal to n square h square by 4 pi mz square. In that you can put over R2 is equal to 2 square h square by 4 pi square mze square. In case of R3 is equal to 3 square h square by 4 pi square mze square. Okay. These are for R2 and R3. Therefore, R2 by R3 ratio we have to go for. R2 by R3. If R2 by R3 ratio you are taking h square common, 4 pi square common, m common, z common, e square. Entire terms will be cancelled out. Only the leftover will be 2 square by 3 square. R2 by R3 is equal to 2 square by 3 square. 2 square means 4. 3 square means 9. So that R3, if you want to calculate, R3 is equal to 9 by 4 R2. Let me repeat. R3 is equal to 9 by 4 R2. This is for what? The radius of third Bohr orbit. Radius of the third Bohr orbit. If radius is known to you, just a reciprocal will become its energy 4 by 9 E2. So it will be 4 by 9 E2. there is a formula. In order to go for the complete calculation, we have the formula. Energy of orbital in a third Bohr's orbit is energy of the electron in the third Bohr's orbit is given by E3 is equal to minus 13.63 square electron volts. After the calculation, the value will be minus of 1.5111 electron volts. This is the general terminology. But if radius is known to you, its reciprocal will become its energy. So that for question number 6, option number 3 is the correct answer. By this, we entirely completed the session and gone with the entire complicated session. We can say today so many questions got solved over and problematic session taken into the consideration, and the most informative questions got covered over. For sure, these are the questions are repeated for so many times in the coming competitive and entrance examinations, so that go with the session very carefully and practice the questions more number of times so that you can achieve for the good practicing skills, and whatever problematic or any kind of question is given to you, you can easily solve that. Practice only most important in the chemistry, especially either it may be organic chemistry, we have to practice the mechanisms. If the physical chemistry, we have to practice the formulas and subsequently how to solve them. And in case of inorganic chemistry, diagrams to be practiced a lot. So this is the way entire chemistry required to be most practicing session. Instead of listening, practice will give the highest content to you. That's the reason why. So go with the content very thoroughly, and really it is more informative for your coming examinations. Like the channel, and in order to comment, we have a question for you, right? So the question is related with the question is regarding, I'll ask the question based on colligative properties. If you count the colligative properties, okay, so what is the formula for depression in the freezing point? What is the formula in order to calculate depression in the freezing point? So that can be, the formula can be simply commented in the comment box for this session, and share with the aspirants who are very serious about the preparation or else any kind of examination, so that you can share with them. It will be helpful for their preparation. Subscribe the channel so that we will go for the new content, new way of content representation as well, and definitely it will be more helpful for your coming examinations, right? So thank you for watching.